This is Sleepy Space, a slow space story to help you fall asleep. Tonight, we're going to explore something that will change the way you think about where you are. Not just your location on Earth, but your place in the cosmos. We're going to discover just how small Earth really is. And I'm not talking about comparing it to nearby planets or the Sun. I'm talking about the true scale. The scale that makes our world almost vanish from sight. Because here's what most people don't understand. Earth isn't just small. It's so incredibly tiny that finding the right words to describe it becomes nearly impossible. By the end of this journey, you're going to see our planet and yourself in a completely different way. Before we begin, if you enjoy these explorations of space and our cosmic perspective, a like or subscribe would help this channel grow. It's a small gesture that makes a real difference. Now, let's start. Let's begin with Earth itself. Our home, the planet we walk on every day. From down here on the surface, Earth seems enormous. You could spend your entire life traveling and still not see every corner of it. The continents stretch for thousands of miles in every direction. The oceans cover about 71% of the surface. Mountains rise nearly 6 miles into the sky. Valleys cut deep into the crust. Rivers wind for thousands of miles from source to sea. To the earliest humans, Earth was everything. It was the entire universe. The ground beneath their feet was the foundation of reality. The sky above was just a dome decorated with lights. The stars were small, perhaps holes in the fabric of the heavens. The sun and moon were objects that moved across this dome, lighting the world by day and night. Earth itself was flat, stretching endlessly in all directions until it reached some distant edge. This made complete sense based on what they could observe. When you stand anywhere on Earth and look toward the horizon, the surface does appear flat. The curvature is too gentle to notice without climbing very high or traveling very far. Earth has a diameter of about 8,000 miles at the equator. If you wanted to walk all the way around the equator, assuming you could somehow walk across the oceans, you'd cover roughly 25,000 miles. At a steady pace of 3 miles per hour, walking 8 hours each day, that journey would take you about 3 years. That's a genuinely long walk. It would take you across deserts and mountains, through forests and grasslands, over frozen tundra and steaming jungles. You'd experience every climate zone. You'd cross every time zone multiple times. 3 years of continuous travel just to return to where you started. The surface area of Earth totals about 197 million square miles. Think about that for a moment. If you wanted to visit every single square mile and spent just 1 second in each location, it would take you over 6 years of continuous travel without stopping, without sleeping, without pausing for even a moment. That's how much surface exists on Earth. The United States, one of the largest countries, covers only about 4 million square miles. That's less than 2% of Earth's total surface. All the land humans have ever walked on, all the cities we've built, all the farms we've cultivated, all of it exists on just under 30% of the planet's surface. The rest is ocean. From our perspective down here, Earth is genuinely enormous. You can spend decades exploring and still discover new places. You can dedicate your life to traveling and never see everything. Mountains take days to climb. Oceans take weeks to cross. Deserts stretch beyond sight. the planet feels infinite in its variety and expanse. Mount Everest, the tallest mountain on Earth, rises about 5.5 miles above sea level. Standing at the base and looking up, it seems impossibly high. The summit exists in a zone where the air is so thin that humans can barely breathe. Climbers take weeks to ascend, acclimatizing slowly to the altitude. Many never make it. Some never return. The mountain has killed hundreds of people who attempted to reach its peak. It represents the extreme edge of where humans can survive on Earth's surface. The oceans, meanwhile, reach depths of nearly 7 miles at their deepest points. The Mariana Trench, the deepest place on Earth, descends further below sea level than Everest rises above it. The pressure at that depth would instantly crush any human body. Only specially designed submersibles can reach it. The bottom exists in perpetual darkness, in waters just above freezing, in an environment as hostile to life as the surface of another planet. And yet life exists even there. Strange creatures adapted to crushing pressure and total darkness. Earth's biosphere extends from the deepest ocean trenches to the highest mountain peaks, a vertical range of over 12 miles. These dimensions matter because they establish scale. They give us a sense of Earth's size from a human perspective. Earth is large enough that early humans could genuinely believe it was infinite. Large enough that even today, with aircraft and highways and centuries of exploration, most people will only ever see a tiny fraction of its surface. Large enough that walking from one side to the other would consume years of your life. But perspective changes everything. And the first shift in perspective happens when we step back just far enough to see Earth alongside its closest companion in space. The Moon orbits Earth at an average distance of about 239,000 miles. That's roughly the distance you'd travel if you drove around Earth's equator almost 10 times. It seems far, and it is far by human standards. When the Apollo astronauts traveled to the Moon in the late 1960s and early 1970s, the journey took them about 3 days each way. 3 days of traveling through empty space at speeds no human had experienced before, just to reach our nearest neighbor. The Moon itself has a diameter of about 2,160 miles. That's roughly 1/4 of Earth's diameter, so the Moon is smaller than Earth, but not dramatically so. If you imagined Earth as a basketball, the Moon would be approximately the size of a tennis ball. They're different sizes, certainly, but they're at least comparable. You can hold both in your mind as objects of roughly similar scale. But here's what's interesting and what most people don't realize. The distance between Earth and the Moon is about 30 times Earth's diameter. Imagine placing 30 Earths in a line, one after another, stretching from our planet to the Moon. That's how much empty space exists in that gap. Most pictures you've seen of the Earth and Moon together don't show this accurately. They usually depict them much closer than they actually are, simply because showing the real distance would make the image impractical. You'd need a very long poster or a very small Earth to fit both objects and the space between them. The reality is that there's an enormous amount of nothing between us and our closest neighbor. This is our first hint that space is mostly empty. Even in our immediate cosmic neighborhood, the distances are vast compared to the sizes of the objects themselves. The Moon isn't sitting just beyond our atmosphere. It's separated from us by a gulf that would take years to walk across if walking through space were somehow possible. The Moon's relationship with Earth is actually quite unusual in our solar system. Most moons are tiny compared to their parent planets. They're essentially captured asteroids or small balls of ice orbiting much larger worlds. But our moon is relatively large compared to Earth. In fact, some astronomers refer to the Earth and Moon system as a double planet because the Moon is so substantial relative to its host. The Moon contains about 1/100th of Earth's mass. That might not sound like much, but it's significant enough to affect Earth in measurable ways. The Moon creates the tides we experience every day. As it orbits Earth, its gravity pulls on our oceans, causing them to bulge slightly toward the Moon, and also away from it on the opposite side. This creates the regular rise and fall of sea levels that coastal communities have relied on for thousands of years. Without the Moon, Earth would still have tides caused by the Sun, but they'd be much weaker. The Moon's tidal effects also gradually slow Earth's rotation. Days are getting longer, though imperceptibly so in a human lifetime. The Moon also helps stabilize Earth's axial tilt. Earth is tilted about 23.5 degrees relative to its orbit around the Sun. This tilt gives us our seasons. Without the Moon's gravitational influence, Earth's axis might wobble dramatically over time, swinging through large angles over thousands or millions of years. This would cause extreme climate variations that could make complex life difficult or impossible to maintain. The Moon acts as a stabilizer, keeping Earth's tilt relatively constant. Looking at the Moon from Earth, it appears about the same size in the sky as the Sun. This is a complete coincidence. The Sun is about 400 times larger than the Moon, but it's also about 400 times farther away. These two factors cancel out almost perfectly, making the Sun and Moon appear nearly identical in size from our perspective. This coincidence gives us total solar eclipses, where the Moon passes directly in front of the Sun and blocks it completely. The Moon's disk fits almost perfectly over the Sun's disk, creating one of nature's most spectacular displays. The Moon is also slowly drifting away from Earth. Each year, it moves about 1.5 inches farther away. This happens because of tidal interactions between Earth and Moon. As Earth's rotation slows due to tidal friction, angular momentum is transferred to the Moon, causing its orbit to expand gradually. Billions of years ago, the Moon was much closer. Days were much shorter, perhaps only 5 hours long. The Moon loomed much larger in the sky. Tides were far more extreme. Over time, as the Moon drifted outward and Earth's rotation slowed, we arrived at the current configuration. For now, the Moon remains our closest companion in space. It's the only other world humans have ever walked on. In 1969, Neil Armstrong and Buzz Aldrin became the first people to set foot on another celestial body. Over the following 3 years, 10 more astronauts walked on the lunar surface. They collected rocks, took photographs, conducted experiments, and proved that humans could travel beyond Earth and return safely. The Moon was our first step into the larger universe. But the Moon, despite its importance to Earth and to human exploration, is small. And the distance to it, while vast by human standards, is tiny compared to other distances in space. The gap between Earth and Moon could fit about 30 Earths. But there are gaps in space that could fit thousands of Earths, millions of Earths, distances so large that Earth's diameter becomes meaningless as a unit of measurement. The Moon taught us that space contains vast stretches of emptiness. But to truly understand scale, we need to look at the object that dominates our sky and makes all life possible: the Sun. The Sun has a diameter of about 864,000 miles. That's 109 times larger than Earth's diameter. If you could somehow hollow out the Sun and fill it with Earths, you could fit approximately 1.3 million of them inside. Think about that for a moment. Every mountain, every ocean, every city, every person who has ever lived. All of human history happened on a planet whose entire volume represents less than 1/1,000,000th of the Sun's interior. The Sun contains 99.86% of all the mass in our solar system. Everything else, all the planets, all the moons, all the asteroids and comets combined, makes up only about 0.14%. The Sun isn't just the largest object in our neighborhood. It's essentially the only object of significance by mass. Everything else is cosmic debris orbiting this massive ball of fusing hydrogen. The Sun sits about 93 million miles away from Earth. Astronomers call this distance one astronomical unit. It's a convenient measurement for distances within our solar system. Light from the Sun takes about 8 minutes and 20 seconds to reach us. If the Sun suddenly vanished, we wouldn't know for over 8 minutes because the light telling us it's gone would still be traveling toward us. We'd continue to see it shining normally for those final minutes, unaware that the source had disappeared. To grasp this distance in human terms, consider that a car traveling at highway speeds would require about 176 years to cover this 93 million mile gulf. You'd need multiple generations of drivers, each passing the journey to the next, to complete the trip. The fastest spacecraft humans have built, the Parker Solar Probe, takes months to reach the Sun's vicinity, even though it's traveling at speeds exceeding 400,000 miles per hour at its closest approach. That's roughly 500 times faster than highway driving, and it still takes months. The Sun is actually a fairly ordinary star. Astronomers classify it as a G-type main sequence star, sometimes called a yellow dwarf. It's about 4.5 billion years old, roughly middle-aged in stellar terms. It has enough hydrogen fuel to keep burning for another 5 billion years or so before it begins to die. When that time comes, it will expand into a red giant, likely engulfing the inner planets, including Earth. But that's far in the future, an almost incomprehensible span of time from now. The Sun's power output is staggering. Every second, it converts about 600 million tons of hydrogen into helium through nuclear fusion. This process releases an enormous amount of energy. The Sun produces more energy in 1 second than all of human civilization has produced throughout its entire history. All our power plants, all our vehicles, all our fires and machines and electrical grids combined, operating continuously since the dawn of humanity, wouldn't equal what the Sun outputs in a single moment. The surface of the Sun has a temperature of about 10,000 degrees Fahrenheit. That's hot enough to vaporize any material we know of instantly. But the core, where fusion occurs, reaches about 27 million degrees Fahrenheit. The pressure at the core is about 260 billion times Earth's atmospheric pressure. Under these extreme conditions, hydrogen nuclei are forced together despite their natural electromagnetic repulsion, fusing into helium and releasing energy in the process. this energy works its way outward over thousands of years, eventually radiating into space as light and heat. The Sun also produces solar flares and coronal mass ejections. These are enormous releases of energy and matter from the Sun's atmosphere. A single large flare can release energy equivalent to millions of nuclear bombs. When these eruptions are directed at Earth, they can cause beautiful auroras near the poles as charged particles interact with our atmosphere. But they can also disrupt satellites, damage power grids, and interfere with communications. In 1859, a massive solar storm called the Carrington event caused auroras visible as far south as the Caribbean and disrupted telegraph systems worldwide. A similar event today would cause trillions of dollars in damage to our technology-dependent civilization. Looking at the Sun reminds us that Earth is not the center of the solar system. For most of human history, people believed Earth was at the center of everything. The Sun, Moon, planets, and stars all revolved around us. This geocentric model seemed obvious. After all, we don't feel Earth moving. The ground feels stationary beneath our feet. The Sun appears to move across the sky, rising in the east and setting in the west. Why wouldn't we be the fixed center? It took brilliant thinkers like Copernicus, Galileo, and Kepler to demonstrate that Earth actually orbits the Sun, not the other way around. Earth is just one planet among several, all circling this central star. We're not special in terms of position or significance within the solar system. We're simply one world at a particular distance from the Sun, following the same laws of gravity and motion that govern everything else. The Sun makes Earth seem small. When you realize that over 1 million Earths could fit inside the Sun, when you understand that the Sun contains almost all the mass in our entire solar system, Earth's significance shrinks considerably. We're a tiny rocky planet orbiting an enormous ball of fusing gas. Without the Sun, Earth would be a frozen, dead world drifting through darkness. Every plant, every animal, every breath of oxygen, every bit of food we eat, all of it depends on energy from the Sun. And yet, the Sun itself is just one ordinary star. There's nothing special about it. It's not particularly large or small, not especially hot or cool, not unusually bright or dim. It's thoroughly average in almost every way. The only reason it seems significant to us is because we orbit it. If the Sun makes Earth seem small, the other planets in our solar system provide an even broader context. Because while Earth might feel substantial to us, it's actually one of the smaller worlds orbiting the Sun. Mercury and Mars are both smaller than Earth, though not dramatically so. Mercury, the closest planet to the Sun, has a diameter of about 3,000 miles. That's roughly 38% of Earth's diameter. Mars, the next planet beyond Earth, has a diameter of about 4,200 miles, roughly half of Earth's. These are smaller worlds, certainly, but they're at least comparable in scale. You can imagine them as smaller versions of Earth, rocky planets with solid surfaces you could theoretically stand on. Venus, meanwhile, is nearly Earth's twin in size. Its diameter is about 7,500 miles, just slightly smaller than Earth's 8,000-mile diameter. If you saw Venus and Earth side by side, you'd be hard-pressed to tell which was larger without careful measurement. But while Venus matches Earth in size, it's radically different in almost every other way. Its atmosphere is thick with carbon dioxide, creating a runaway greenhouse effect that keeps the surface at about 900 degrees Fahrenheit. The atmospheric pressure at the surface is about 90 times Earth's. It rains sulfuric acid. The planet rotates backward compared to most other planets, and a single day on Venus lasts longer than a Venusian year. These four rocky planets, Mercury, Venus, Earth, and Mars, represent the inner solar system. They're all relatively small, all made primarily of rock and metal, all with solid surfaces. They orbit relatively close to the Sun. Mercury takes about 88 Earth days to complete one orbit. Venus takes about 225 days. Earth takes 365 days by definition. Mars takes about 687 days. These are worlds you could reach with chemical rockets in a matter of months. They exist within a region of space that humans could theoretically explore directly. But beyond Mars, past the asteroid belt, the solar system changes completely. The gas giants introduce an entirely new scale. Jupiter, the fifth planet from the Sun, has a diameter of about 89,000 miles. That's 11 times Earth's diameter. Jupiter's volume could contain over 1,300 Earths. If you hollowed out Jupiter and started filling it with Earth-sized spheres, you could fit all of them inside with room to spare. Jupiter contains more than 300 times Earth's mass. In fact, Jupiter is more massive than all the other planets combined. If you added up the mass of every other planet, moon, asteroid, and comet in the solar system except the Sun, Jupiter would still be more than twice as massive. Jupiter doesn't have a solid surface like Earth. It's composed primarily of hydrogen and helium, the same elements that make up the Sun, though not in high enough concentrations or temperatures to trigger fusion. If you could somehow descend into Jupiter, you'd pass through layers of increasingly dense gas until eventually the pressure would be so intense that the hydrogen would behave more like liquid metal than gas. There might be a small rocky core at the center, but we're not certain. The Great Red Spot, a storm system in Jupiter's atmosphere, is larger than Earth. This storm has been raging for at least 350 years, possibly much longer. It's a hurricane that would swallow our entire planet. Jupiter spins faster than any other planet in the solar system, completing one rotation in about 10 hours despite its enormous size. This rapid rotation creates powerful winds and dramatic banding patterns in the atmosphere. Saturn, the sixth planet, is slightly smaller than Jupiter but still enormous compared to Earth. It has a diameter of about 75,000 miles, roughly 9.5 times Earth's diameter. Saturn could contain about 760 Earths inside its volume. But Saturn is perhaps most famous for its magnificent ring system. These rings span about 175,000 miles across, but are remarkably thin, only about 30 feet thick in most places. If you scaled Saturn's rings down to the size of a football field, they'd be thinner than a piece of paper. The rings are made of countless chunks of ice and rock, ranging from tiny particles to house-sized boulders. They orbit Saturn in a flat disk, held in place by the planet's gravity and shaped by the gravitational influences of Saturn's many moons. The rings are probably temporary on cosmic timescales, perhaps only a few 100 million years old, and they'll likely disappear within another 100 million years or so, as the material gradually falls into Saturn's atmosphere. Uranus and Neptune, the seventh and eighth planets, are ice giants. Each is about 4 times Earth's diameter. Uranus has a diameter of roughly 32,000 miles, Neptune is slightly smaller at about 31,000 miles. Both are made primarily of water, methane, and ammonia ices surrounding rocky cores. These are strange, cold worlds orbiting in the outer reaches of the solar system. Uranus is tilted so extremely that it essentially rolls along its orbital path, with its poles pointing almost directly at the Sun during the parts of its orbit. Neptune, the farthest planet, orbits at about 2.8 billion miles from the Sun. That's about 30 times Earth's distance from the Sun. Light takes about 4 hours to travel from the Sun to Neptune. If you stood on Neptune's surface, assuming it had a surface to stand on, the Sun would appear as just a bright star in the sky, giving only about 1/900th the light it provides to Earth. These outer worlds exist in perpetual twilight, cold and dark, and impossibly distant. The solar system's organization reveals a pattern. The rocky inner planets are small and close together. The gas and ice giants are enormous and spread across vast distances. Earth, positioned third from the Sun, occupies a region sometimes called the habitable zone, where temperatures allow liquid water to exist. But in terms of size, Earth is unremarkable. It's one of the smaller planets, dwarfed by the giants beyond Mars. The planets show us that Earth is small compared to its siblings, but the solar system extends far beyond Neptune. There's a vast region of space still bound to the Sun's gravity, filled with smaller objects that define the true edge of our cosmic neighborhood. Beyond Neptune lies a region called the Kuiper Belt. This is a vast zone of icy bodies orbiting the Sun at enormous distances. The Kuiper Belt begins at about 30 astronomical units from the Sun, roughly where Neptune orbits, and extends outward to approximately 50 astronomical units. Remember, 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So the Kuiper Belt stretches across a region that's billions of miles wide. Pluto orbits within the Kuiper Belt. For decades, Pluto was considered the 9th planet, the most distant member of our planetary family. But in 2006, astronomers reclassified it as a dwarf planet. This wasn't a demotion so much as a recognition that Pluto is just one object among thousands in the Kuiper Belt. It has a diameter of about 1,400 miles, smaller than Earth's moon. Other dwarf planets orbit in this region as well. Eris, Makemake, Haumea, and many others. Some are similar in size to Pluto. Some are smaller. They're all frozen worlds, barely touched by the Sun's warmth at that distance. The New Horizons spacecraft, launched in 2006, took 9.5 years to reach Pluto. 9.5 years of traveling through empty space at speeds approaching 36,000 miles per hour. When it finally arrived in 2015, it sent back the first close-up images of Pluto's surface. The photos revealed a surprisingly complex world with nitrogen ice plains, water ice mountains, and a thin atmosphere that freezes and falls to the surface as snow when Pluto moves farther from the Sun in its elliptical orbit. But even Pluto's distance doesn't represent the edge of the solar system. Beyond the Kuiper Belt lies something called the scattered disk. This is a region where objects follow highly elliptical orbits that take them far beyond the Kuiper Belt's outer edge before swinging back toward the Sun. Some of these objects spend most of their time in the outer reaches, only occasionally coming close enough to be visible from Earth. They're scattered, as the name suggests, spread across a vast volume of space rather than confined to a relatively flat disk, like the planets and Kuiper Belt objects. And beyond even that, there's the Oort cloud. This is a theoretical spherical shell of icy objects surrounding the entire solar system. We say theoretical because we've never directly observed the Oort cloud. It's too far away and its objects are too small and dark to see with our telescopes. But we infer its existence from the comets that occasionally fall inward toward the Sun. Long-period comets, the ones that take thousands or millions of years to complete a single orbit, seem to come from all directions in space. This suggests they originate from a spherical cloud rather than a flat disk. The Oort cloud is thought to extend from about 2,000 astronomical units to as far as 100,000 astronomical units from the Sun. At its outer edge, it reaches about 1.6 light-years from the Sun. That's roughly 1/3 of the distance to the nearest star. The Oort cloud marks the true gravitational boundary of the Sun's influence. Beyond it, the Sun's gravity becomes too weak to hold objects in orbit. They drift away into interstellar space, no longer part of our solar system. This region, the Oort cloud, may contain trillions of objects. Most are probably smaller than mountains, chunks of ice and rock left over from the solar system's formation 4.5 billion years ago. They've been orbiting out there in the cold and dark ever since, barely moving, barely changing, preserved in deep freeze. Occasionally, a passing star's gravity or a random gravitational interaction will nudge one of these objects, sending it falling toward the inner solar system. As it approaches the Sun and heats up, it develops a tail of vaporizing ice, becoming what we call a comet. Travel time through this region would be enormous with current technology. Even moving at the speed of the New Horizons spacecraft, reaching the inner edge of the Oort cloud would take centuries. Reaching the outer edge would take tens of thousands of years. These are timescales that exceed human lifespans by many generations. We could send a probe toward the Oort cloud, but the people who launched it, their children, their grandchildren, and many generations after them would all be gone before the probe arrived. The solar system we're discovering is much larger than the region containing the planets. The 8 planets orbit within about 30 astronomical units of the Sun. That seems like a vast distance, and it is by human standards. But it represents only a tiny inner circle within the Sun's full sphere of gravitational influence. The Oort cloud extends more than 3,000 times farther out. If you drew the solar system to scale with Earth's orbit as a circle 1 inch in diameter, the Oort cloud would extend out over 1/2 mile in all directions. This region is mostly empty. The distances between objects are enormous even here. If you stood on a Kuiper Belt object and looked around, you probably wouldn't see another object with your naked eye. The sky would be black and filled with stars, just as it is when viewed from Earth, but colder and darker because the Sun would appear as merely a bright star among others. You'd be alone in the darkness, orbiting slowly through the outer reaches of our solar system. Earth's orbit, the path our planet follows around the Sun, lies deep within this vast structure. We orbit at 1 astronomical unit, while the solar system extends 100,000 astronomical units. We're not even close to the edge. We're near the center, in a relatively crowded region where planets and asteroids orbit the Sun. Beyond that lies emptiness, cold and dark and immense, before you finally reach the true boundary of our solar system. Our solar system, vast as it is, represents just one tiny bubble of space around one ordinary star. To understand Earth's true scale, we need to venture beyond the Sun's influence and encounter the nearest stars. The distances that separate them will redefine everything we've learned so far. The nearest star to our Sun is called Proxima Centauri. It sits about 4.24 light-years away. That's roughly 25 trillion miles. To put that in perspective, using the measurements we've been using, Proxima Centauri is about 268,000 astronomical units from us. Remember, 1 astronomical unit is the distance from Earth to the Sun. The nearest star is 268,000 times farther away than our own star. Voyager 1, launched in 1977, is currently the most distant human-made object. It's traveling at about 38,000 miles per hour, moving through interstellar space beyond the edge of our solar system. At this speed, Voyager 1 would take about 75,000 years to reach Proxima Centauri. That's assuming it were headed in that direction, which it's not. 75,000 years is longer than all of recorded human history. It's longer than modern humans have existed as a species. You could launch a spacecraft toward Proxima Centauri today, and it wouldn't arrive until long after our current civilization has risen and fallen, perhaps multiple times. Some scientists have proposed more ambitious missions. The Breakthrough Starshot project envisions using powerful lasers to push tiny spacecraft equipped with light sails, accelerating them to about 20% the speed of light. At that speed, the journey to Proxima Centauri would take around 20 years. But even this represents an enormous technological challenge. We don't currently have lasers powerful enough or spacecraft light enough to make this work. And 20% the speed of light is still unimaginably fast, far beyond anything we've achieved with chemical rockets or any other propulsion system we currently use. Proxima Centauri is part of a triple star system called Alpha Centauri. The other 2 stars, Alpha Centauri A and Alpha Centauri B, are slightly farther away, but orbit each other, with Proxima Centauri orbiting both of them at a great distance. These are our nearest stellar neighbors, 3 stars bound together by gravity, slowly orbiting their common center of mass. Other nearby stars scatter across space in our local neighborhood. Barnard's star lies about 6 light-years away. Wolf 359 sits about 7.5 light-years distant. Sirius, the brightest star in Earth's night sky, is about 8.5 light-years away. These are the stars closest to us. They define our immediate stellar environment. Most of these nearby stars are dim red dwarfs, much smaller and cooler than our Sun. They're not visible to the naked eye despite being relatively close. Proxima Centauri itself is a red dwarf. If you looked at it from Earth without a telescope, you wouldn't see it at all. It's too faint. Sirius is one of the few nearby stars bright enough and large enough to be prominent in our sky. Most of the stars you can see on a clear night are actually very distant but extremely luminous. They're visible not because they're close, but because they're intrinsically bright enough to be seen across great distances. The average distance between stars in our region of the galaxy is about 4 to 5 light-years. Sometimes stars pass closer together, sometimes they're farther apart, but this represents a typical separation. Stars are isolated islands separated by vast oceans of empty space. The space between stars contains almost nothing. Occasionally, a stray hydrogen atom drifts through the void. Sometimes there's a bit of dust, but mostly it's vacuum, emptiness, darkness stretching for trillions of miles. This is where the light year becomes a necessary unit of measurement. A light year is the distance light travels in 1 year. Light moves at about 186,000 miles per second. In 1 year, traveling at that speed without stopping, light covers about 6 trillion miles. That's 1 light year. It's an enormous distance, but it's also the minimum practical unit for measuring distances between stars. Using miles becomes meaningless at this scale. The numbers are too large to comprehend. Looking up at the night sky from Earth, every star you can see with your naked eye is relatively nearby. Most visible stars lie within about 1,000 light years of Earth. That sounds far, and it is far beyond anything we can currently travel. But it represents only our immediate cosmic neighborhood. The brightest stars in familiar constellations, Betelgeuse, Rigel, Deneb, they're all within this rough boundary. They're our neighbors in cosmic terms. If you could shrink distances so that the Sun became a grain of sand, Proxima Centauri would be another grain of sand about 4 miles away. The space between them would contain nothing but air in this scaled-down model. No other grains of sand, no other objects, just empty space stretching for miles. And Earth, at this scale, would be invisible. It would be far smaller than a grain of sand. It would be smaller than a bacterium. It would effectively cease to exist as a visible object. The distances between stars dwarf everything we've discussed so far. The 93 million miles from Earth to the Sun seemed vast when we first considered it. The billions of miles from the Sun to the Kuiper Belt seemed incomprehensible. But the 25 trillion miles to Proxima Centauri makes all those distances seem trivial. It's a different scale entirely, a scale where even our entire solar system shrinks to insignificance. And these nearby stars aren't randomly scattered through empty space. They're organized. They're part of something much larger, a structure so vast that our journey from Earth through the solar system to nearby stars represents an invisibly small region within it. These nearby stars, scattered across light years of space, are all part of something much larger. They're not randomly distributed through the universe. They're organized into a structure so vast that our entire journey through the solar system and to nearby stars represents an invisibly small region within it. We're talking about our galaxy. The Milky Way is a spiral galaxy. It has a central bulge surrounded by a flat disk of stars arranged in spiral arms that curve outward from the center. The galaxy's disk measures approximately 100,000 light-years across. That's the distance light would travel in 100,000 years, moving continuously at 186,000 miles per second. The disk is relatively thin compared to its width, only about 1,000 light-years thick in most places. The central bulge is thicker, extending about 13,000 light-years above and below the disk's plane. Our galaxy contains somewhere between 200 billion and 400 billion stars. The exact number is uncertain because many stars are too dim to count directly, and dust clouds block our view of some regions. But that's the current estimate based on the stars we can observe and statistical models of what we can't see. Each of those stars is a sun, potentially with its own system of planets and moons. The Sun sits about 26,000 light-years from the galactic center. We're not near the center where stars crowd together densely. We're not at the outer edge where stars thin out and eventually peter out into intergalactic space. We're about halfway out in a relatively average location. Our Sun orbits within the Orion Arm, sometimes called the Orion Spur. This is a minor spiral arm, a smaller branch between two larger arms called the Perseus Arm and the Sagittarius Arm. The Sun orbits the galactic center at about 514,000 miles per hour. That seems incredibly fast, and it is by any human standard. But the distance around the galactic center is so enormous that even at this speed, one complete orbit takes about 230 million years. Astronomers sometimes call this a galactic year. The last time the Sun was at its current position in the galaxy, Earth was in the Triassic period. Dinosaurs hadn't evolved yet. The continents were joined together in a single landmass called Pangaea. Since then, the Sun has traveled completely around the galaxy and returned to where it started. The galactic center contains a supermassive black hole called Sagittarius A star. This black hole has a mass about 4 million times the Sun's mass. It sits at the gravitational center of the galaxy, with all the stars orbiting around it. We can't see the black hole directly because no light escapes from it, but we can observe stars near the galactic center following tight orbits around an invisible point, their motion revealing the presence of an enormous mass, concentrated in a tiny region of space. The galaxy's spiral arms are regions of higher stellar density and active star formation. Stars throughout the galaxy orbit the center at different speeds depending on their distance. Stars closer to the center orbit faster. Stars farther out orbit slower. This differential rotation causes the spiral pattern. The arms aren't fixed structures that rotate as solid objects. Instead, they're density waves moving through the galaxy. Stars drift into the arms, slow down slightly due to gravitational interactions, then drift back out. The arms persist, while individual stars move through them. Most of the galaxy's stars concentrate towards the center. The central bulge is bright and crowded. Stars there orbit in random directions rather than following the organized rotation of the disk. The outer regions of the galaxy are dimmer and less crowded. Stars there are spread farther apart. Eventually, at the galaxy's edge, the density of stars drops off, and you reach intergalactic space, the vast darkness between galaxies where stars are rare or absent. The galaxy has what astronomers call a habitable zone, regions where conditions are favorable for planets that might support life. Too close to the galactic center, radiation levels are high. Supernovae explode frequently in the dense stellar environment. Black holes and neutron stars create dangerous conditions. Too far from the center, there aren't enough heavy elements. The first generation of stars contained only hydrogen and helium. All the heavier elements, carbon, nitrogen, oxygen, iron, were created in stars and scattered into space when those stars died. Regions with mostly old stars don't have enough of these heavy elements to form rocky planets. The Sun orbits in a relatively calm region, far enough from the center to avoid excessive radiation, close enough that heavy elements were available when the solar system formed. We're also between spiral arms, in a relatively empty space where supernovae are less common. This might be important for life. A nearby supernova could bathe Earth in lethal radiation. By existing in a quieter region, Earth has avoided this fate for billions of years. When you look up at the night sky on a dark, clear night, you can see the Milky Way stretching across the heavens as a band of dim light. This is our galaxy seen from inside. You're looking edge-on through the disk, seeing millions of stars too distant and dim to resolve individually. They blend together into a soft glow. That glow is your view of the galactic plane from our position within it. The dark patches in the Milky Way aren't regions with no stars. They're dust clouds blocking the light from stars behind them. Every star visible to your naked eye is part of the Milky Way. Every constellation, every planet you can see, every galaxy visible without a telescope except for Andromeda, it all belongs to our galaxy. The Milky Way is your cosmic home, the structure you're embedded within. And at this scale, Earth has essentially vanished. The solar system itself is invisible. Individual stars merge into vast collections. The distance from Earth to the Sun, which seemed so enormous when we started, now represents essentially zero on the scale we're considering. The Milky Way seems incomprehensibly large, and it is, by any standard we've used so far. But the universe doesn't stop at our galaxy's edge. In fact, our galaxy is just one among a vast number, scattered across space at distances that make interstellar travel seem trivial by comparison. The Andromeda Galaxy, also known as Messier 31, is the nearest large spiral galaxy to the Milky Way. It sits about 2.5 million light-years away. That's the distance light travels in 2.5 million years. The photons of light entering your eye when you look at Andromeda began their journey before modern humans existed. They've been traveling through empty space for over 2 million years, crossing the vast gulf between galaxies, finally arriving at Earth where your eye happens to catch them. Andromeda is actually larger than the Milky Way. It spans approximately 220,000 light-years across, more than twice the diameter of our galaxy. It contains roughly 1 trillion stars, also more than our galaxy's estimated 200 to 400 billion. Andromeda is visible to the naked eye from dark locations, appearing as a small, fuzzy patch of light in the constellation it's named after. Most people who see it don't realize they're looking at another galaxy, a separate island of hundreds of billions of stars floating in space. Andromeda and the Milky Way are moving toward each other. They're approaching at about 250,000 miles per hour. In about 4 billion years, they'll collide. This won't be a violent crash in the way collisions usually work. Stars are so far apart that individual stars will almost certainly not hit each other. Instead, the two galaxies will pass through each other, their stars intermixing, their spiral structures disrupted by gravitational interactions. Over hundreds of millions of years, they'll merge into a single larger galaxy, probably an elliptical galaxy rather than a spiral. The Sun and Earth will likely survive this merger, simply finding themselves in a different galaxy with a different shape and structure. The Milky Way and Andromeda are the two dominant members of what's called the local group. This is a gravitationally bound collection of galaxies, all relatively close together, all orbiting their common center of mass. The local group contains the Milky Way, Andromeda, and a smaller spiral galaxy called Triangulum, along with about 80 dwarf galaxies. These dwarf galaxies are much smaller, containing anywhere from a few billion stars down to just a few million. The Large Magellanic Cloud and Small Magellanic Cloud are two dwarf galaxies visible from Earth's southern hemisphere. They appear as cloudy patches in the night sky, like detached pieces of the Milky Way. For a long time, people didn't realize they were separate galaxies. They thought they were just unusually bright regions of our own galaxy. Only in the 20th century did astronomers determine these clouds were actually satellite galaxies orbiting the Milky Way, separate stellar systems bound to us by gravity. The local group spans about 10 million light-years across. Within this volume, these 80 or so galaxies orbit each other, held together by mutual gravitational attraction. Beyond the local group, the next major concentration of galaxies lies tens of millions of light-years away. Between galaxy groups, space is relatively empty. You might find an occasional stray galaxy, a loner drifting through intergalactic space. But mostly, there's nothing. Just vast expanses of darkness dotted here and there with distant galaxy groups. Intergalactic space is even emptier than interstellar space. Between stars, you occasionally find a hydrogen atom or a grain of dust. Between galaxies, even these sparse traces of matter become rare. The average density of matter in intergalactic space is about 1 hydrogen atom per cubic meter. That's essentially perfect vacuum by any practical definition. Light travels through this emptiness for millions of years without encountering anything substantial enough to scatter or absorb it. The galaxies within groups are relatively close together by cosmic standards. They interact gravitationally. Larger galaxies pull on smaller ones, sometimes capturing them and consuming them over billions of years. Spiral galaxies passing near each other can trigger waves of star formation as their gravitational interactions compress gas clouds. Sometimes galaxies collide and merge, combining their stars into larger structures. These processes drive galactic evolution, changing the shapes and sizes of galaxies over cosmic time. Our position in the local group is somewhat peripheral. The Milky Way and Andromeda are the two largest members, and they dominate the group's gravity. We're not at the center of the local group. We're offset, one of two major galaxies with a collection of smaller satellites orbiting around us. Triangulum is the third largest spiral, but it's considerably smaller than either the Milky Way or Andromeda. The rest are dwarf galaxies, small collections of stars that exist in the gravitational shadow of their larger neighbors. Looking at the local group from outside, if you could somehow position yourself far enough away to see the entire structure at once, you'd see a collection of glowing spots scattered across about 10 million light-years of space. The two brightest spots would be the Milky Way and Andromeda, with Triangulum as a smaller but still significant point of light. The dwarf galaxies would be dimmer, some barely visible. And between all these glowing points, darkness. Vast stretches of empty space separating these islands of light. At this scale, individual stars have long since become invisible. You can't see the sun anymore. You can't distinguish individual stars at all. You can only see entire galaxies, collections of hundreds of billions of stars appearing as single, glowing objects. Earth, which seemed so large when we started this journey, is now so far beyond visibility that its absence is total. It doesn't exist at this scale, not as something you could identify or point to. It's buried within a galaxy, invisible, insignificant, lost in the vastness. The local group represents our immediate galactic neighborhood. But this small cluster is just one tiny region in a much larger structure that organizes galaxies across hundreds of millions of light years. We're approaching the scale where Earth's position becomes genuinely difficult to describe. The Virgo cluster is the nearest major galaxy cluster to us. It sits about 65 million light-years away, much farther than our local group neighbors. The Virgo cluster contains over 1,300 galaxies, spanning roughly 15 million light-years of space. This is a dense concentration of galaxies, far more crowded than the relatively sparse local group we belong to. At the center of the Virgo cluster sits a massive elliptical galaxy called Messier 87. This galaxy is enormous, much larger than the Milky Way. It contains several trillion stars. At its center lies a supermassive black hole with a mass of about 6.5 billion times the Sun's mass. That's over 1,500 times more massive than the black hole at the center of the Milky Way. In 2019, astronomers captured the first ever direct image of a black hole's event horizon, the boundary beyond which nothing can escape. That image showed the black hole at the center of Messier 87, a dark circle surrounded by a glowing ring of superheated matter spiraling inward. The Virgo cluster represents a major concentration of mass in our region of the universe. Its gravity affects galaxies across vast distances. In fact, our local group, despite being tens of millions of light-years away, is slowly falling toward the Virgo cluster. We're not orbiting it in any simple sense, and we'll probably never actually merge with it, but its gravitational influence extends far enough to pull on us, affecting our motion through space. Our local group is actually part of something larger called the Virgo supercluster, though astronomers sometimes call it the local supercluster. This is an enormous structure containing many galaxy clusters, including both our local group and the Virgo cluster. The Virgo supercluster spans about 110 million light-years across. It contains approximately 47,000 galaxies in total. Our local group sits near the outer edge of this supercluster, not anywhere near the center where the Virgo cluster dominates. The discovery that superclusters exist came relatively recently in astronomical history. Through the 1950s, 60s, 70s, and 80s, as galaxy surveys became more comprehensive and astronomers mapped larger and larger regions of space, they realized that galaxy clusters weren't randomly scattered. They were organized into even larger structures. These structures, superclusters, represented a new level of cosmic organization that hadn't been recognized before. The Coma cluster is another major galaxy cluster sitting about 300 million light-years away. It contains over 1,000 galaxies concentrated in a region about 20 million light-years across. Like the Virgo cluster, the Coma cluster represents a major concentration of mass, dominating its local region of space. Between major clusters like Virgo and Coma, the density of galaxies drops. Space isn't uniformly filled with galaxies. They clump together in clusters, and clusters group into superclusters, with vast stretches of relatively empty space between these concentrations. These structures form because of gravity. Over billions of years, gravity pulls matter together. Small variations in density in the early universe, tiny fluctuations in how matter was distributed, grew over time as gravity amplified them. Regions that were slightly denser attracted more matter, becoming denser still. This positive feedback created the structure we see today, with matter concentrated into galaxies, galaxies concentrated into clusters, and clusters organized into superclusters. Between superclusters lie cosmic voids. These are enormous regions containing very few galaxies. Some voids span hundreds of millions of light years. They're not completely empty, you might find occasional galaxies within them, but they're far emptier than the supercluster regions. The contrast between dense regions full of galaxy clusters and nearly empty voids creates a pattern that astronomers call the cosmic web. When you map the positions of millions of galaxies in three-dimensional space, a pattern emerges. Galaxies aren't spread uniformly like stars in a galaxy. They're arranged in filament-like structures, walls and sheets and threads of galaxies surrounding vast, empty voids. The overall pattern resembles a sponge or foam, with dense regions forming the structure and voids representing the empty spaces. This is the large-scale structure of the universe, the organization of matter on the largest scales we can observe. The cosmic web formed through the gravitational collapse of matter over billions of years. Computer simulations can recreate this process. You start with a nearly uniform distribution of matter with tiny random variations in density. You let gravity operate over billions of simulated years. The simulation produces structures that match what we observe in the real universe. Filaments form, voids appear. Galaxy clusters concentrate at the intersections of filaments. The simulation and observation agree, confirming our understanding of how gravity shapes the universe at large scales. Earth's location can now be described more fully. We orbit the Sun, a star in the Milky Way galaxy. The Milky Way belongs to the local group of galaxies. The local group sits near the edge of the Virgo supercluster. And the Virgo supercluster is one structure among many in the cosmic web. Each level of organization is vastly larger than the last. Each step outward makes the previous scale seem tiny. At this level, individual galaxies begin to fade from view. When you map out superclusters, you're no longer tracking individual galaxies. You're measuring the statistical distribution of galaxies, counting how many appear in each region of space. Individual galaxies become data points, too numerous to examine one by one. The Milky Way, which seemed so vast when we examined it closely, now represents a single point in a vast map of cosmic structure. And Earth, our starting point, has vanished completely from any meaningful description. We're looking at structures containing thousands of galaxies, each containing hundreds of billions of stars, each potentially hosting countless planets. Earth is buried somewhere in this immensity, invisible, undetectable, lost in scales that render individual planets meaningless. At this scale, Earth has effectively vanished. We're looking at structures containing thousands of galaxies, each with hundreds of billions of stars, each potentially with countless planets. But even superclusters are not the largest structures we've discovered. The universe organizes itself into even larger patterns. In 2014, astronomers announced the discovery of an even larger structure, containing the Virgo supercluster. They called it Laniakea, which means immeasurable heaven in Hawaiian. Laniakea is a supercluster of superclusters, a vast gravitationally bound region spanning about 520 million light-years across. It contains the mass equivalent of about 100,000 trillion suns. That's a 1 followed by 17 zeros worth of solar masses, concentrated across a region of space so large that light takes over 500 million years to cross it. The discovery of Laniakea came from mapping how galaxies move. Galaxies aren't stationary. They orbit within their clusters. Clusters move relative to other clusters, and all of this motion reveals the underlying gravitational structure. By carefully measuring the velocities of thousands of galaxies, astronomers could determine which direction each galaxy was moving and how fast. These motions revealed that galaxies across an enormous region were all being pulled toward a common gravitational center. Everything within this region, including the Virgo supercluster and our local group, belongs to Laniakea. Within Laniakea, there's a region called the Great Attractor. This is a gravitational anomaly, a region of space that seems to be pulling nearby galaxy clusters toward it. For decades, astronomers knew something massive must exist in that direction because they could measure its gravitational influence on other galaxies. But the Great Attractor lies behind the plane of the Milky Way from our perspective, hidden behind dust and stars that block our view. We still don't fully understand what's there, but it appears to be a massive concentration of galaxy clusters creating a gravitational pull strong enough to affect structures across hundreds of millions of light years. Beyond Laniakea, astronomers have identified other massive structures. The Sloan Great Wall is an enormous concentration of galaxies spanning about 1.37 billion light-years in length. It's one of the largest known structures in the universe. The wall isn't solid, of course. It's a region where galaxies are more densely concentrated than in surrounding space, forming a sheet or wall-like structure of matter with voids on either side. The Hercules Corona Borealis Great Wall might be even larger, potentially spanning about 10 billion light-years. Though some astronomers debate whether this structure truly exists as a single entity, or whether it's a statistical artifact of how we map galaxy distributions. If it is real, it challenges something called the cosmological principle, the idea that the universe should look roughly the same in all directions at large enough scales. Structures this large seem to violate that principle, suggesting the universe might not be as uniform as we thought. The cosmic web becomes clearly visible when you survey millions of galaxies across billions of light-years. Deep surveys like the Sloan Digital Sky Survey have mapped the positions of hundreds of millions of galaxies, creating three-dimensional maps of cosmic structure. These maps reveal filaments of galaxies stretching across space, connecting clusters and superclusters. The filaments surround enormous voids, regions where galaxies are rare. These voids can be hundreds of millions of light-years across. The Bootes void, discovered in 1981, spans about 330 million light-years. It contains very few galaxies, perhaps only 60 where you'd expect to find about 10,000 based on the average density of galaxies in the universe. Standing in the center of the Bootes void, if you could somehow be there, you'd see almost no galaxies in any direction. The nearest galaxies would be hundreds of millions of light-years away, too distant and too dim to see without powerful telescopes. The sky would be almost completely black, devoid of the distant galaxy light that fills the sky when viewed from regions of normal density. These structures, the filaments and voids and great walls, formed from tiny quantum fluctuations in the moments after the Big Bang. In the earliest instance of the universe, random quantum variations created slight differences in density from place to place. These variations were incredibly small, less than 1 part in 100,000. But over billions of years, gravity amplified these tiny differences. Regions slightly denser than average attracted more matter. Regions slightly less dense lost matter to their denser neighbors. Over time, this process created the cosmic web we see today. Dark matter plays a crucial role in forming this structure. Dark matter is matter that doesn't emit, absorb, or reflect light. We can't see it directly, but we can detect its gravitational effects. Dark matter appears to make up about 85% of all matter in the universe. Its gravity shapes the cosmic web, pulling ordinary matter into the patterns we observe. Computer simulations that include dark matter produce structures matching what telescopes see. Simulations without dark matter fail to produce the right patterns. At this scale, individual galaxies become invisible. When you map structures spanning billions of light years, you can't see individual galaxies anymore. You can only see statistical distributions counting how many galaxies appear in each region of space. The Milky Way, with its hundreds of billions of stars, becomes a single data point in these maps. One galaxy among hundreds of millions being counted and positioned. And Earth, somewhere in that single galaxy, has long since ceased to exist as anything measurable or meaningful at this scale. The cosmic web represents the largest structures gravity can create. Beyond this scale, the universe's expansion begins to dominate over gravitational attraction. Structures larger than superclusters don't have time to form because the expansion of space pulls distant regions apart faster than gravity can pull them together. The cosmic web represents the limit of structure, the largest organization matter achieves in our universe. We've traveled from Earth through our solar system, past nearby stars, across our galaxy, through clusters and superclusters, to see the largest structures in the universe. But we haven't yet addressed the universe's total size. To do that, we need to understand what we can actually see and why there's a limit to our vision. The observable universe is the region of space from which light has had time to reach us since the Big Bang. The current diameter of the observable universe is approximately 93 billion light-years. That's the distance light traveling for 93 billion years would cover. But here's something that confuses people. The universe is only about 13.8 billion years old. How can we see objects 93 billion light-years away if light has only been traveling for 13.8 billion years? The answer is that space itself has been expanding. When light left distant galaxies billions of years ago, those galaxies were much closer to us than they are now. The light began its journey across a shorter distance. But as the light traveled toward us, the space between us and those galaxies expanded, stretching out the distance. By the time the light reaches us, the galaxy that emitted it has been carried far away by the expansion of space. The expansion doesn't affect the speed of light, but it does increase the distance between objects over time. Distant galaxies are receding from us. The farther away a galaxy is, the faster it appears to be moving away. This is because space itself is expanding everywhere. More space between us and a distant galaxy means more expansion happening in that space, which translates to a higher apparent velocity. The most distant galaxies are receding faster than the speed of light. This doesn't violate relativity because the galaxies aren't moving through space faster than light. Space itself is expanding, carrying the galaxies with it. There's a boundary to what we can see, a cosmic horizon. Beyond this boundary, light hasn't had time to reach us yet. The universe might extend far beyond what we can observe, possibly infinitely, but we can never see beyond the observable region. As time passes, this boundary expands as light from more distant regions reaches us. But the expansion of space also carries distant galaxies away, and some galaxies are receding so fast that their light will never reach us, no matter how long we wait. Current estimates suggest the observable universe contains approximately 2 trillion galaxies. That's 2,000 billion galaxies, each containing anywhere from a few million to several trillion stars. If we assume an average of 100 billion stars per galaxy, though this varies enormously, the total number of stars in the observable universe is roughly 10 to the power of 24. That's a 1 followed by 24 zeros. Some people call this number a septillion, and the number of planets is likely several times higher than the number of stars. Most stars probably have at least one planet. Many stars have multiple planets. The exact ratio is still being determined as we discover more exoplanets, but a conservative estimate would put the number of planets at several times the number of stars. That means tens of septillions of planets exist in the observable universe. The Hubble Space Telescope's deep field observations revealed just how densely packed the universe is with galaxies. In the mid-1990s, astronomers pointed Hubble at a tiny patch of apparently empty sky, a region about the size of a grain of sand held at arm's length. They exposed the image for over 10 days, collecting every photon they could from that tiny region. When they processed the image, they found nearly 3,000 galaxies in that one small patch. Later, the Hubble Ultra Deep Field pushed even deeper, revealing about 10,000 galaxies in a similarly tiny region. What this tells us is that every direction we look, no matter how empty the sky appears, contains thousands or millions of galaxies if we look deeply enough. The darkness between visible stars isn't empty. It's filled with galaxies so distant and dim that we need powerful telescopes and long exposures to see them. Point a telescope anywhere and you'll find galaxies. The universe is full of them in every direction. The universe beyond the observable region is likely infinite or near infinite. We can never observe it because its light hasn't reached us and never will due to expansion. But there's no reason to think the universe just stops at the edge of what we can see. The observable universe is a sphere centered on Earth, defined by the distance light can travel in the age of the universe, accounting for expansion. But an observer in a distant galaxy would have their own observable universe, a sphere centered on their location. Parts of their observable universe would overlap with ours, but parts wouldn't. They could see things we can't, and we can see things they can't. The cosmological principle suggests the universe looks roughly the same everywhere at large scales. There's no special center, no edge, no unique location. The observable universe appears uniform in all directions when you average over large enough scales. This suggests the universe beyond what we can see is probably similar to what we observe. More galaxies, more stars, more planets, extending perhaps forever. Earth's location within this vastness is completely unremarkable. We're not near the center of the observable universe because there is no center. The observable universe is defined by our position as observers, not by any physical center point. An observer anywhere else would see themselves at the center of their own observable universe. We occupy no special position. We're simply one planet, around one star, in one galaxy, in one small region of a universe so vast that our entire observable sphere might be just a tiny bubble within something much larger. At this scale, even our local supercluster vanishes from significance. Laniakea, spanning over 500 million light-years, represents less than 1% of the observable universe's diameter. It's a local feature, a nearby structure that seems important to us, but disappears in the vastness when you consider the full extent of what exists. Now we can finally comprehend Earth's true scale. We've moved from our planet to our solar system, to nearby stars, to our galaxy, to clusters and superclusters, and finally to the observable universe. Let's put this journey into perspective with concrete comparisons that show just how small Earth really is. If the observable universe were shrunk down to the size of Earth, the Milky Way galaxy would be approximately the size of a single human cell. You couldn't see it without a microscope, and Earth at this scale would be far smaller than an atom within that cell. Earth would be smaller than the nucleus of that atom. It would be smaller than a proton within that nucleus. Earth would effectively cease to exist as a measurable object. It would vanish completely, too small to register at any scale you could meaningfully discuss. Here's another way to think about it. If the sun were the size of a white blood cell, something about 0.008 of a millimeter across, the Milky Way galaxy would span approximately the width of the United States. And the observable universe at this same scale would extend out to somewhere around Pluto's orbit in our actual solar system. These scaled comparisons help illustrate the nested levels of size we're dealing with, but they still struggle to capture the full extent of the disparity. Earth's volume compared to the Sun represents about 9/10 millionths of 1%. That's a decimal point followed by 6 zeros, and then a 9. The Sun's volume compared to the volume of the Milky Way is infinitesimally smaller still. And the Milky Way compared to the observable universe is vanishingly tiny. When you multiply these ratios together, Earth represents approximately 1 part in 10 to the power of 60 of the observable universe's volume. That's a 1 with 60 zeros after it in the denominator. There's no human scale analogy that can capture this ratio. It's beyond meaningful comparison. Let's try looking at time instead of space. If you compress the entire age of the universe, about 13.8 billion years, into a single calendar year, Earth would form on September 1st. The solar system condensed from a cloud of gas and dust about 4.5 billion years ago, roughly 1/3 of the way through the universe's current age. For the first 8.5 billion years of the universe's existence, Earth didn't exist. In this compressed calendar, the first life on Earth would appear around September 15th. Simple single-celled organisms emerged about 3.5 to 4 billion years ago, not long after Earth's surface cooled enough to support liquid water. For most of Earth's history, life was simple. Just bacteria and archaea, microscopic organisms with no complex structures. Complex multicellular life wouldn't appear until much later. The Cambrian explosion, when most major animal groups first appeared in the fossil record, would happen around December 13th in our compressed calendar. Dinosaurs would emerge on December 26th. They'd dominate the planet for the next few days until an asteroid impact on December 30th caused a mass extinction, wiping them out along with about 3/4 of all species on Earth. Modern humans, Homo sapiens, would appear in the last 2 minutes before midnight on December 31st. All of recorded human history, everything from the earliest written records to today, would occur in the final few seconds before the year ends. The entire span of human civilization, all the empires and kingdoms and nations, all the wars and discoveries and achievements, compressed into mere seconds in this cosmic calendar. Every person who has ever lived, every thought that's ever been thought, every emotion that's ever been felt, it all happened on one tiny planet during those final seconds. The pyramids of Giza were built about 3 seconds before midnight. The Roman Empire rose and fell in the last 2 seconds. The Renaissance, the Industrial Revolution, both world wars, the space age, the digital revolution, all of human technological advancement happened in the last fraction of a second. When you consider Earth's size in the context of the observable universe, the numbers become absurd. The observable universe contains approximately 2 trillion galaxies. Each galaxy contains an average of perhaps 100 billion stars. That's 200 billion trillion stars total, though estimates vary. If we assume a similar number of planets, which is conservative since many stars have multiple planets, we're looking at hundreds of billions of trillions of worlds. Earth is one planet among this incomprehensible multitude. Every human conflict, every war ever fought, every piece of land ever disputed, all of it took place on one world among hundreds of billions of trillions. We fought wars over tiny fractions of Earth's surface, pieces of land representing infinitesimal fractions of 1% of our planet. And our planet represents an infinitesimal fraction of the universe. All the resources we've ever competed for exist on Earth. All the territory we've ever claimed, all the borders we've drawn, they divide up one small rocky planet that represents essentially 0% of the universe's volume. From a cosmic perspective, the things we fight over are absurdly small. We're dividing up something that barely exists when measured against the scale of what's out there. And yet, everything meaningful to us happened here. Every person you've ever known lived on Earth. Every place you've ever been exists on this planet. Every book ever written, every song ever sung, every painting ever created, all of it came from this tiny world. The entirety of human culture, all our art and science and philosophy, all our love and conflict and cooperation, it all arose on this invisible speck. The mathematical reality of Earth's size compared to the universe is clear. We're unimaginably small, but mathematical smallness doesn't necessarily equate to insignificance. Size is one way to measure importance, but it's not the only way. A thought has no size, no mass, no volume. Does that make thoughts unimportant? An idea can change the world despite having no physical dimensions at all. These comparisons show Earth's physical insignificance. But they also raise profound questions. If we're this small, this isolated, this brief in cosmic terms, what does it mean? Should we feel diminished? Or is there something else to consider about our place in this vast universe? The automatic emotional response to cosmic scale is to feel small and insignificant. When you realize that Earth represents essentially 0% of the universe's volume, when you understand that all of human history occupies mere seconds on a cosmic calendar, when you grasp that we're invisible at any scale larger than our immediate stellar neighborhood, the natural reaction is to feel diminished. What possible importance could we have in all this vastness? But scale alone doesn't determine importance or value. A diamond is small, a grain of sand is small, they're roughly the same size. But we don't value them equally. Size doesn't tell you everything about significance. What matters isn't just how much space something occupies, but what that something is and what it does. Earth might be tiny, but it's the only place we know with life. And not just simple life, not just bacteria or single-celled organisms, but complex, multicellular life, plants and animals, ecosystems spanning the entire planet, millions of species interacting in intricate webs of dependency and competition. Earth has produced forests and coral reefs and savannas and tundras. It has produced whales and redwood trees and fungi networks that stretch for miles underground. The biosphere that exists on Earth is, as far as we know, unique in the entire observable universe. And beyond just life, Earth has produced consciousness, beings that are aware of their own existence, animals that can think and feel and remember and plan. And among those conscious beings, Earth has produced intelligence, tool-using, language-speaking, technology-building intelligence. Humans are not the only intelligent species on Earth. Other animals show problem-solving abilities, use tools, communicate with each other, demonstrate self-awareness. But humans have taken intelligence to a level that allows us to understand the universe itself. We've built telescopes that can see billions of light years across space. We've developed mathematics that can describe how galaxies form and how stars die. We've figured out that Earth orbits the Sun, that the Sun orbits the galactic center, that our galaxy is one among trillions. We understand the Big Bang, we know the age of the universe. We've mapped cosmic structure across billions of light years. We've done all this despite being confined to one tiny planet for our entire existence as a species. This raises a question that astronomers call the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The universe contains billions of galaxies, each with hundreds of billions of stars. Many of those stars have planets. The number of potentially habitable worlds is staggeringly large. If life is common, if intelligence is common, if technological civilizations are common, then where are they? Why haven't we detected any signs of other civilizations? Why haven't they visited us or sent signals we can detect? There are many possible answers. Maybe life is rare. Maybe the conditions needed for life to emerge are so specific, so unlikely, that Earth might be one of very few life-bearing worlds. Maybe life is common, but intelligence is rare. Perhaps most planets with life never develop complex organisms. Maybe intelligence is common, but technological civilizations are rare. Most intelligent species might never develop technology beyond basic tools. Or maybe technological civilizations are common, but brief. Maybe every species that reaches our level of technology faces challenges that lead to extinction. Climate change, nuclear war, artificial intelligence gone wrong. resource depletion, pandemics. Maybe the window between developing technology and destroying yourself is very narrow. Maybe the galaxy is full of civilizations that rose and fell, none of them lasting long enough to explore beyond their home systems. We don't know which answer is correct, but the fact that we haven't detected anyone else is significant. It suggests that whatever we are, we're not common. Life, intelligence, consciousness, technology, some combination of these things is rare enough that we haven't found neighbors, despite decades of searching. Earth has accomplished something remarkable. It has produced beings who can understand the cosmos. We are literally the universe becoming aware of itself. The atoms in your body were forged in stars that died billions of years ago. When those stars exploded, they scattered their contents across space. That material eventually condensed into new stars and planets, including our Sun and Earth. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it came from stellar furnaces. You're made of star stuff. As astronomer Carl Sagan famously said, but you're not just star stuff. You're star stuff that has organized itself into a structure capable of contemplating its own origins. The universe has been around for nearly 14 billion years. For most of that time, it was just matter following physical laws. Atoms and photons and forces interacting in ways that can be predicted and calculated. But somewhere along the way, in at least one location that we know of, matter organized itself into living things. And those living things eventually organized themselves into conscious observers, capable of asking questions about where they came from. The improbability of our existence is staggering. We orbit at the right distance from the right type of star. Too close, and Earth would be too hot. Too far, and it would be too cold. Our star is stable, not prone to dangerous flares that would sterilize the planet. We have a large moon that stabilizes our axial tilt, preventing extreme climate swings. We have Jupiter in the outer solar system, whose gravity deflects many asteroids and comets that might otherwise hit Earth. We have a magnetic field generated by Earth's molten iron core, protecting us from solar radiation that would otherwise strip away our atmosphere. We exist at the right time in cosmic history. Too early and there wouldn't be enough heavy elements to form rocky planets. Stars in the first few generations after the Big Bang were made only of hydrogen and helium. All heavier elements had to be created in stars and distributed through space when those stars died. We needed several generations of stars to live and die before there was enough carbon and oxygen and silicon to build Earth. The sheer luck of being here at all is almost incomprehensible, and yet here we are, small beyond measure but also, possibly, precious beyond measure. Understanding our cosmic insignificance in scale but potential significance in rarity leads to a sobering realization. If we are rare or unique, then our choices matter enormously. What we do on this tiny planet might have cosmic implications. If consciousness is rare in the universe, then Earth's biosphere has cosmic value. We might be the only location for hundreds of millions of light years, possibly billions of light years, where matter has organized itself into thinking, feeling beings. Every species on Earth represents millions of years of evolution, uncountable generations adapting to their environment, surviving and reproducing despite constant challenges. When a species goes extinct, that entire lineage disappears. all the evolutionary innovations that species developed, all the unique adaptations, gone forever. From a purely terrestrial perspective, extinction is tragic but local. One species among millions disappears. The ecosystem adjusts. New species eventually fill the vacant ecological niche. Life continues. But if Earth is the only world with life, or one of very few, then every extinction isn't just a local loss. It might be a universal loss, a form of life that will never exist again anywhere in the cosmos. Human conflicts seem absurd when viewed from a cosmic perspective. We divide Earth into nations and fight wars over borders. We compete for resources and territory. We draw lines on maps and defend them with violence. But we're not fighting over a large territory. We're fighting over different parts of a dust speck. We're not competing for the resources of a vast world. We're competing for the resources of something almost too small to measure against cosmic scales. All our borders, all our nations, all our political divisions, they're meaningful to us because they affect our lives. They determine where we can live, what laws apply to us, what rights we have. These things matter on human terms. But they're meaningless to the universe. The cosmos doesn't care about our borders. Space doesn't recognize our claims of sovereignty. From outside Earth, looking at our planet from a distance, you can't see borders. You can't see nations. You only see one world, one interconnected biosphere, one thin film of life coating a rocky sphere. Climate change and environmental destruction take on a different character when you remember we're on the only known life-bearing world. We're not just damaging our environment. We might be damaging the only environment in a vast region of space where complex life exists. If we render Earth uninhabitable, if we destroy the biosphere or make it incapable of supporting technological civilization, we might be silencing consciousness in this entire corner of the universe. The responsibility of being potentially alone is enormous. We can't know for certain whether life exists elsewhere. We can't know if intelligence and consciousness are common or rare. But until we find evidence of life beyond Earth, we have to act as if what happens here matters enormously. Earth might be precious beyond measure, the only world where matter became aware of itself, where the universe opened its eyes and looked at itself. But there's also potential, the possibility of spreading beyond Earth. Humanity has existed for roughly 300,000 years. We've been technologically advanced for only a few centuries. We've been spacefaring for only about 70 years. We've sent 12 people to the moon's surface. We've sent robotic probes to every planet in the solar system. We've landed rovers on Mars and sent a probe into interstellar space. These are just first steps, baby steps into the cosmos, but they're steps. Our long-term future could span millions or billions of years if we survive the next few centuries. The universe will remain hospitable to life for an incomprehensibly long time. Stars will continue burning for trillions of years, though most will be small red dwarfs rather than sun-like stars. Planets will continue orbiting. The laws of physics that allow complexity to exist will remain in force. The universe isn't ending anytime soon. If humanity survives and spreads beyond Earth, if we learn to live sustainably or expand to other worlds, we could potentially outlive not just our planet, but our sun. When the sun eventually expands into a red giant about 5 billion years from now, humanity or its descendants could be living elsewhere, watching from a safe distance. We could witness the gradual evolution of our galaxy, see stars being born and dying, watch as the Milky Way and Andromeda merge into a new galactic structure over billions of years. Our descendants might spread beyond the Milky Way to other galaxies. They might develop technologies we cannot imagine, ways of traveling or communicating across vast distances. They might transform themselves, merging with machines or adopting new forms better suited to life in space or in extreme environments. They might seed the galaxy with life, taking Earth's biosphere and replicating it on thousands or millions of other worlds, spreading the phenomenon of life throughout regions of space that are currently dead. Or we might fail. Civilizations might be fragile, brief sparks of consciousness that flicker and die on cosmic timescales. We might destroy ourselves through war, through environmental collapse, through technologies we develop faster than we develop the wisdom to use them responsibly. We might be facing challenges right now that determine whether humanity has a long future or a short one. The Great Filter is a concept in discussions about extraterrestrial life. It suggests there's some challenge, some barrier that prevents civilizations from becoming advanced spacefaring species. Either that filter is behind us, meaning the emergence of life or intelligence is incredibly rare and difficult, or the filter is ahead of us, meaning something prevents most technological civilizations from surviving long enough to spread beyond their home planets. If the filter is behind us, if life and intelligence are the rare parts, then we've already passed the hardest challenge. Our future could be long and expansive. But if the filter is ahead of us, if technological civilizations typically destroy themselves, then we're approaching the most dangerous period in our history. The next few centuries might determine whether humanity joins the countless other civilizations that failed to survive their technological adolescence, or whether we become one of the rare species that makes it through. The choice, to the extent we have one, is ours. Earth is tiny. Our individual lives are brief. But the cumulative effect of billions of humans making choices, developing technology, creating knowledge, and passing it to the next generation has brought us to this moment. We're the first species on Earth capable of comprehending the cosmos. We're also the first capable of either spreading life beyond our planet or extinguishing it entirely. Understanding our cosmic insignificance in scale but potential significance in rarity leads to a sobering realization. If we are rare or unique, then our choices matter enormously. What we do on this tiny planet might have cosmic implications. We've covered a lot of ground tonight. Let's bring this exploration to a close with some final reflections. We started this journey on Earth's surface, standing on ground that felt solid and permanent beneath our feet. We began with a planet that seemed enormous, a world so large that you could spend multiple lifetimes exploring it and never see everything. Earth felt substantial. It felt like the center of everything, the stage on which all of human experience plays out. Then we stepped back. We looked at Earth from the moon's distance and saw our planet as one object among two, separated by a gulf of empty space. We stepped back further and saw Earth dwarfed by the sun, a tiny rocky world orbiting an enormous ball of fusing hydrogen. We kept stepping back, watching Earth shrink with each new perspective, past the other planets through the Kuiper Belt, past the edge of the solar system into interstellar space. At each step, the previous scale that seemed so vast became tiny. The distance from Earth to the Sun, which seemed incomprehensibly large when we first considered it, became trivial when compared to interstellar distances. The gap between stars, which seemed impossibly vast, became insignificant when we zoomed out to see the entire galaxy. The galaxy itself, with its hundreds of billions of stars, shrank to a point when we pulled back far enough to see neighboring galaxies. Every level of organization follows the same pattern. Planets orbit stars. Stars cluster into galaxies. Galaxies group into clusters. Clusters organize into superclusters. Superclusters form filaments in the cosmic web. At each scale, gravity operates, pulling matter together into structures. From the smallest scale of planets to the larger scale of galaxy superclusters, the same force shapes everything we see. We've learned our cosmic address. Earth, third planet from the Sun. The Sun, a star in the Orion arm of the Milky Way galaxy. The Milky Way, a member of the local group of galaxies. The local group, part of the Virgo supercluster. The Virgo supercluster contained within Laniakea. Laniakea, one structure among many in the cosmic web. And all of it, every galaxy we can observe, contained within the observable universe, a sphere centered on us only because that's where we happen to be observing from. The dual truth we've discovered is this: we are cosmically insignificant in size. Earth is smaller relative to the universe than an atom is relative to Earth. Our entire galaxy, with its hundreds of billions of stars, represents a tiny fraction of 1% of the observable universe. And the observable universe itself might be just a tiny bubble within something much larger, possibly infinite. But we might also be significant in what we represent. We're possibly the only conscious beings in a vast region of space. The only location where matter has organized itself into structures capable of understanding the cosmos. Life might be common in the universe. We don't know. But the fact that we haven't detected anyone else suggests we're at least rare. And rarity creates value in a way that abundance cannot. Being small doesn't mean being unimportant. A thought has no size, no mass, no volume, but thoughts change the world. Consciousness occupies no space in the physical sense, but it's what makes existence meaningful. Without conscious observers, the universe would simply exist, matter following physical laws, stars being born and dying, galaxies forming and merging. All of it happening without anyone there to witness it or comprehend it or care about it. No other species on Earth can grasp cosmic scale the way humans can. Other animals are intelligent in their own ways. They solve problems, use tools, communicate, form social bonds. But they don't build telescopes. They don't calculate the distances to other galaxies. They don't contemplate their place in the universe. That ability to understand where we are and what surrounds us seems to be unique to humans. And we might be the only beings in our entire region of space with this ability. Looking up at the night sky now means something different than it did before this journey. Those stars you see, you now know they're suns, many with their own planets. That faint band of light stretching across the sky, the Milky Way. You now understand it's our galaxy seen from inside. A view of billions of stars too distant and dim to resolve individually. The darkness between stars, you now know, contains galaxies beyond counting, spread across distances so vast that their light takes billions of years to reach us. You're standing on a tiny world, a world so small it would disappear in any scale model of the universe, a world that represents essentially 0% of the cosmos. But it's the only world we have. It's the only place we know where life exists. It's the only place where consciousness has emerged, where beings can look up and understand what they're seeing. That makes Earth precious despite its size. The universe is vast beyond human comprehension. The distances are so large that even light, traveling faster than anything else can travel, takes billions of years to cross them. The structures are so enormous that entire galaxies become invisible points when you pull back far enough. The numbers are so large that words fail to capture them adequately. And Earth, in all that vastness, is invisible, undetectable, too small to register on any cosmic scale. But Earth is also home. Every human who ever lived was born here, lived here, died here. Every thought ever thought, every emotion ever felt, every relationship ever formed, it all happened on this tiny world. Every book in every library, every song ever sung, every painting ever created, all human culture and achievement and experience confined to one small planet. You can understand this, at least intellectually. You can grasp that the universe is measured in billions of light years, while Earth is measured in thousands of miles. You can comprehend that we're small, beyond any meaningful comparison. That understanding itself is extraordinary. Out of all the planets in all the galaxies, Earth is the one that produced beings capable of comprehending the universe. We might not be alone in this. There might be countless other civilizations scattered across the cosmos, each looking up at their own skies and wondering. But we don't know that for certain. Right now, Earth is the only place we know where consciousness exists. That makes Earth precious beyond measure. Size doesn't determine value. What matters is what's here. And what's here on this tiny planet is something remarkable. Life, consciousness, the ability to wonder, to question, to seek understanding. Thank you for joining me on this journey across the cosmos. If you found this exploration meaningful, a like or subscribe would help this channel continue making these deep dives into space and our place in it. Remember, you're standing on a planet that's tiny beyond comprehension when compared to the universe. But you're also standing on the only world we know that's home to life, consciousness, and wonder. Sleep well under the stars tonight. The universe is enormous, Earth is tiny, but Earth is precious. And you, living on this small world, are part of its story. Good night.